Hello, I am Seong-Eun, a researcher at the IIIXR lab. Today, I will introduce a paper titled Training Diffusion Model with Reinforcement Learning, published at IIIXR 2024. This paper introduces a method for fine-tuning a pre-trained large-scale diffusion model using reinforcement learning to enhance its performance on downstream tasks. To demonstrate this approach, the author used a text-based image generation diffusion model and fine-tuned it with the PPO algorithm. For the reward function, they utilized a vision language model called LAVA. First, the pre-trained diffusion model generates an output image based on an input text. Then the generated image, along with the prompt, what is happening in this image, is fed into the VLM to produce an output text. As a result, we obtain the output image text, while we obtain the input text of the diffusion model and the output text from LAVA. To define the reward based on the similarity between these two texts, the paper employs BART score. To optimize the multi-step denoising process, an important sampling estimator is used. Additionally, to prevent excessive deviation from the previous policy, a trust region implemented with clipping is applied to constrain the update size. For detailed equation, please refer to the paper. Thank you for listening to my presentation.
Today, I will introduce two different approaches for tool-augmented reasoning, REACT and AVATAR. REACT, which stands for reasoning and acting, alternates between thinking and taking action. It retrieves and processes information step by step. However, it has several limitations. First, it struggles to break down complex queries into actionable steps. Second, it often relies on simple string matching, which leads to inefficient tool uses. Lastly, this results in inconsistent performance, especially for multi-step reasoning tasks. AVATAR addresses these issues by introducing contrastive reasoning. It learns effective tool uses by comparing failure cases with successful ones. Instead of relying on static prompts, AVATAR continuously optimizes prompts dynamically. More importantly, it doesn't just use one retrieval method. It integrates multi-tools such as embedding similarity for semantic search, token matching for precise filtering, and LLM-based validation to ensure accuracy. To illustrate the difference, let's consider a product recommendation task. Imagine a user asks, "Can you recommend a Tusa swim fin with a split fin design?" A React-based agent would likely perform a basic string search for Tusa swim fins and return a result without checking if they actually have a split fin design. AVATAR, on the other hand, takes a structured approach. It first breaks down the query into brand type and feature attributes. It then applies embedding search to find relevant products, uses token matching to filter for Tusa brand items, and finally leverages on LLM validation step to check if the fins truly have a split fin design. By combining weighted scores from these steps, AVATAR ensures the recommendation is accurate and relevant. In summary, AVATAR outperforms REACT by systemically learning from past mistakes, dynamically optimizing its prompts, and integrating multiple retrieval methods. This results in more precise, efficient, and adaptable design making. Thank you.
Today, I will introduce research on human-scene interaction, which aims to create more realistic virtual environments through interactions between 3D human models and scenes. The paper I will discuss is titled GP-HSI and was published in TOMM in 2025. Traditional methods often consider only the spatial distance between human models and the scene, neglecting the vertical relationships between the contact surfaces of the models. Additionally, the absence of explicit mechanisms for collision detection and pose assessment has led to problems with model penetration. This approach limits the physical plausibility of interactions in certain situations. To address these issues, GP-HSI applies geometric and physical constraints that consider the vertical relationships between the human model and contact object surfaces, and uses an inverse kinematics based on pose assessment to enable physically plausible interactions. The framework includes three main steps. First, it optimizes the semantic levels of the human model through pose-guided semantic generation. Second, it applies geometric and semantic constraints to appropriately place the human model within the scene. Third, it uses an IK-based pose assessment to finely tune the model's pose, enhancing the quality of interaction. Thank you for listening.
Hello, my name is Joohyun Park. The paper I'd like to introduce in this section is PointLLM, Empowering Large Language Models to Understand Point Clouds. By now, many of you are familiar with large language models and their remarkable ability to understand and process text, excelling in tasks like question answering. However, despite their strong reasoning capabilities, LLMs struggle to interpret 3D data, which is a crucial component in various industries, including computer graphics. While there have been attempts to incorporate 3D spatial understanding into LLMs, most of these efforts rely on 3D multi-view images, which fail to fully preserve the original 3D structure. This limitation hinders the true integration of spatial reasoning within LLMs. PointLLM aims to address this gap by introducing a point cloud projector and fine-tuning the LLM for answering 3D related questions. As illustrated in the left image, the process begins with encoding the point cloud into latent representations using a pre-trained model, PointBERT. However, since these representations exist in a different space from the LLMs, a projector model is used to convert them into tokens that the LLM can understand. Once transformed, these tokens, along with a corresponding 3D related question, are fed into the LLM. The LLM's output is then compared with ground truth answers during training. Throughout this process, the LLM acquires the ability to comprehend and reason about point cloud data. As shown in the right image, the trained model demonstrates the capability to answer a wide range of questions that require an understanding of 3D structures.
Hello, my name is DongHeun. I will be introducing the paper titled Synchronize Dual Hands for Physics-Based Dexterous Guitar Playing at SIGGRAPH Asia 2024. This paper introduces a new technique for generating coordinate motions in physics-based simulations with a focus on virtual guitar playing. It presents a bimanual control method where each hand functions as an independent agent. In the first page, the individual control poses for each hand are trained separately using reinforcement and imitation learning, allowing each hand to develop dexterous skills for tasks like fret pressing for the left hand and string picking for the right hand. Once these skills are mastered, the authors then synchronize the two separate hand controllers through latent space manipulation in a centralized learning environment, leading to finely coordinated bimanual motions. By leveraging this two-stage approach, the method avoids the complications of training a single joint policy over a high-dimensional joint state action space, significantly improving training efficiency. The effectiveness of the technique is demonstrated by training a virtual guitarist who can play songs with a wide variety of rhythms, chord patterns, and techniques simply by processing input guitar tabs. Here's an example of this agent playing the legendary rock and roll song Johnny B. Good by Chuck Berry.
Hello, my name is SeungJeh in IIIXR lab. Today I'll introduce Mip-Splatting, a method presented at CBPR 2024 that addresses aliasing issues in zoom-in and zoom-out scenarios of 3D Gaussian splatting. To begin with, 3D Gaussian splatting inherently applies 2D dilation to ensure smooth blending between Gaussians in screen space. This dilation enlarges the projected 2D Gaussian by a fixed factor, mitigating aliasing artifacts, especially in areas with high-frequency details. However, this approach introduces challenges when the camera's focal length changes. First, when zooming out, the focal length decreases, causing the projected 2D Gaussian to shrink. Since dilation is applied as a fixed scaling factor, the relative expansion increases. For example, if a Gaussian initially expands by 4%, a smaller Gaussian in a zoomed-out view might expand by 16%. This makes objects too thicker, increases Gaussian overlap per pixel, and causes brightening artifacts due to too much radiance stacking up. On the other hand, when zooming in, the focal length increases and very small Gaussians that were used to capture fine details become much bigger. Because of this, the dilation effect becomes weaker, making edges look sharper and creating gaps where things were smoothly connected before. As a result, high-frequency artifacts appear. So individual Gaussians become more visible instead of blending together, making surface look less natural. To resolve these issues, Mip-Splatting replaces traditional 2D dilation filters with 2D Mip filters and introducing a 3D smoothing filter that constrains the frequency of Gaussians. By doing so, it reduces aliasing across zoom levels and improves rendering quality by adapting Gaussian properties dynamically.
Hello everyone, today I will introduce a paper titled DiffPoseTalk, Speech-Driven Stylistic 3D Facial Animation and Head Pose Generation via Diffusion Models. Transitional speech-driven 3D facial animation models rely on either deterministic models or one-hot encoding for style representation, but both have limitations. Deterministic models fail to capture the many-to-many relationship between speech and facial representations, leading to average-looking over-smooth animations. One-hot encoding cannot fully capture the complexity of different speaking styles, making it difficult to generalize to unseen styles. This paper introduces a DiffPoseTalk, a diffusion-based model that generates diverse and stylistic 3D facial animations along with natural head movements. The key innovations are first, a style encoder that extracts a style embedding from a short reference video instead of using one-hot vector, allowing for more personalized animations. Second, a diffusion model that enables probabilistic sampling, producing more natural and valid facial motions compared to deterministic models. And third, head pose prediction, which allows the model to generate not just the facial expressions, but also natural head movements, leading to more realistic and engaging animations. The image on the slide shows a qualitative comparison between DiffPoseTalk and existing models. The top row labeled ground truths represent real 3D facial expressions extracted from video data, while the rows below show the outputs of different models. Looking at the highlighted works like changes between and made, we can compare the accuracy of leaf shapes. Existing models such as FaceFormer, CodeFormer, and Face Diffusion often generate less expressive or inaccurate mouse shapes. In contrast, DiffPoseTalk processes more accurate and natural movements that closely resemble the real data. On the right, we see words with like family and Python, and DiffPoseTalk captures the subtle facial details and mouse movements, while other models produce less variation and realism. In summary, DiffPoseTalk overcomes the limitations of previous models, producing more natural, diverse, and stylistic 3D facial animations, including realistic head movements. This approach has potential applications in virtual avatars, animation, and the metaverse. Thank you.
Block diffusion proposes a new approach that divides text into multiple blocks and generates them in a hybrid manner. Traditional autoregressive models predict tokens one by one, achieving high quality but lack parallel generation. On the other hand, diffusion-based models can generate multiple tokens in parallel, but often struggle with variable length sequences and are more complex to train. This paper combines the two methods by adapting a diffusion process within each block, while chaining these blocks in an autoregressive fashion. This design allows for flexible generation of long sequences and leverages parallelism to improve generation speed. Additionally, it retains the controllability of diffusion models, making it easier to customize or constrain intermediate steps. For example, by fixing certain tokens or styles, the experimental results show that block diffusion can match or surpass the quality of standard autoregressive models and offers speed advantages through block-level parallel decoding. This makes it particularly appealing for large-scale text applications, while both high quality and efficient inference are critical. In summary, block diffusion bridges the gap between autoregressive and diffusion-based language models, providing an efficient balance between performance, flexibility, and speed. It's a promising avenue for future research and industrial deployment, especially in scenarios demanding controllable, high-quality text generation.
Hello, this is Ryunha Lee, and I will introduce the paper Exploring Large Language Model-Driven Agents for Environment-Aware Spatial Interactions and Conversations in Virtual Reality Role-Play Scenarios. The paper investigates agents capable of role-playing by responding to spatial interactions and user conversations in real time within a VR environment. However, vision-based agents struggle to fully incorporate role-related information and suffer from significant computational overhead. To address this, the authors developed a more efficient text-based schema that continuously provides LLM agents with information about the VR environment. Additionally, they implemented a VR system using Unity that continuously generates meta information following the schema's format. First, let us focus on the most crucial aspect, the schema architecture. The schema defines 5 main components: system context, objects, characters, spots, and communication. This provides the necessary contextual information for role-play scenarios in the VR environment. The system context component includes 3 subcomponents. System settings define the schema structure, interacting protocols, and the virtual environment's layout. Scenario settings specifies roles, and objectives. Function list defines the available action that agent can perform within the environment. These functions trigger specific animations or interactions, such as walking or picking up objects. The spot components describe specific locations in the virtual environment for interactions. A spot may indicate an idle position for accessing objects, presenting exhibits, or exiting the scenes. Each spot includes its name, position, and direction relative to the agent. The object components consist of two types, objects and containers. Containers are a subcategory of objects which can hold other objects. Each object element includes object names, description, positions, and grabbability, which defines whether an object is fixed or movable. If an object is a container, it also specifies the objects it contains. The character component includes character names, position, direction, and hand states, which define the objects they are holding. This information helps the agent generate human-like behavior and perceive the state of other characters, particularly the user, to facilitate interactions. Finally, the communication component manages action cues and dialogues between characters. Additionally, error messages from the last LLM response are recorded to guide the agent in making valid actions. Now let us explore how the VR simulation utilized this schema to communicate and operate with the LLM agent. The VR environment structures real-time information following the predefined text-based schema architecture and provides it to the LLM agent. The LLM selects an action from the function list within the schema architecture. At this stage, it must correctly specify the spot and object name. The game engine validates the selected function call by checking whether the function, spot, and object states are appropriate. For example, the left-handed grab function requires the agent's left hand to be free, the object to be movable, and within the agent's interaction range. If the action is valid, it passes to the animator, which executes the corresponding animation and iterations. If the action is invalid, an error message is stored and later included in the communication component of the schema. Additionally, the system generates conversation text, which is converted into speech using text-to-speech to simulate natural language interactions. Thanks for watching.
Hello, the paper I will be introducing is Cyclic Test Time Adaptation of Monocular Video on 3D Human Mesh Reconstruction. This paper aims to address the human pose estimation problem. However, my focus will be on introducing test time adaptation and explaining how it is applied in this paper. Test time adaptation is a technique that allows a model to adapt itself during testing. The necessity of these techniques arises because the training data and the test data can be different, and this can mitigate the limitations of data-driven method. There are several approaches to implementing test time adaptation, such as self-supervised learning, entropy minimization, and batch normalization adjustment. However, this paper specifically employs self-supervised learning. And additionally, the paper Beyond Model Adaptation at Test Time survey demonstrates the rapid increase in research related to test time adaptation. So, application of test time adaptation in pose estimation. This method is applied to pose estimation as follows. First, it utilizes the well-known HMR networks. The HMR stands for Human Mesh Recovery. This network will take an image as input and predict XML pose and shape. Next, some frames are masked and forwarded to a pre-trained denoising network. The denoising network reconstructs the pose of the masked frames, and the difference between the reconstructed pose and the input pose is used as a loss to adjust the network. The output of the denoising network is then used to adjust the HMR network. The difference between the HMR network's output and the denoising network's output is used as a loss to update the HMR network. This process is repeated 12 times, ensuring that even if the distribution of test data differs from the training data, the model maintains stable performance and improves the reliability of the output. My presentation ends here, and thanks.
Hello, I'm JaeYoung from IIIXR Lab. Today I'll introduce a method for generating realistic characters in interactions from natural language instructions in 3D environments. Traditional approaches either require separate models for different interaction types, like working, hand reaching, or full human object interaction, or rely on additional user inputs such as object trajectories. These constraints reduce flexibility and make long integrated motion sequences difficult to achieve. This paper proposes 3 core contributions to address these limitations. First, it employs an autoregressive diffusion model, which generates motion in short segments and seamlessly stitches them together. By working segment by segment, the system can handle everything from phasing locomotion to intricate manipulations in a unified way. Second, there's an autonomous scheduler that automatically decides when to transition from one stage of motion to the next stage. So it knows exactly when to switch from, for example, working to picking up an object. Finally, the dual voxel sensor provides local 3D occupancy information both at the character's current position and its target position, helping the model avoid collisions and interact plausibly with scene objects. Altogether, these innovations allow for more coherent, flexible, and robust scene interactions driven purely by text instructions. It's an important step toward more natural, automated character animation in complex 3D spaces.
Hello, my name is Subin Lim. Today I'll be presenting the paper Sting Motion, Generating 3D Human Motions by Drawing a Stingman, which has been accepted to CBPR 2025. Sting Motion proposes a text-to-motion method that incorporates simple Stingman sketches as additional input to better capture user intentions that are difficult to express through text alone. Since hand-drawn Stingman figure data is scarce, the researchers developed the Stingman generation algorithm to automatically generate hand-drawn Stingman. As shown in the figure on the right, this algorithm converts 3D human joint coordinates into Stingman sketches. Additionally, to effectively integrate text and Stingman figure conditions, Sting Motion introduced the multi-condition module MCM. Sting Motion is a diffusion-based model and its architecture is as follows. The input, including Stingman sketches, noised motion, and text, are fed into the multi-condition module. Within the multi-condition module, the model handles 4 different condition combinations: text, stick, and empty conditions. These combinations are assigned to 4 separated batches: B1, B2, B3, and B4. The module consists of 2 feature decoders. One decoder processes only text, and the other decoder processes only Stingman features. The predicted offset from these decoders are then added back to the original encoding. The updated new motion encoding is passed through a latent encoder for further refinement. Compared to conventional approach with self-attention modules that rely on partial masking, MCM reduces computational complexity while achieving superior performance. The final output consists of predicted noise for denoising during the diffusion process, and index score, which determines the frame index while the given stickman drawing is positioned within the generated motion sequence. Stick motion supports stickman figures at 3 different points: start, middle, and end of the motion sequence. The result shows that adding stickman figures improve the alignment of generated motion with user intent compared to using text alone. Thank you.
Hello everyone, I'm Byungmin Kim from IIIXR Lab, and today I'm going to introduce Grip, a novel method for generating realistic hand-object interaction poses using spatial cues and latent consistency. Human hands play a crucial role in object manipulation, yet existing methods often neglect hand motion or focus only on static grasps. Traditional approaches either require complex motion capture setups or rely on optimization techniques that are computationally expensive. Grip overcomes these limitations by taking 3D body and object motion as input and generating realistic dynamic hand movements before, during, and after interaction. Grip consists of 3 main components. An ANet, arm denoising network, cleans noisy arm motion to provide better input. Consistency network, called CNet, predicts the initial hand motion using spatial and temporal features, and RNet, refinement network, refines hand poses to ensure smooth interactions and prevent object penetrations. One of Grip's key innovations is latent temporal consistency called LTC, which maintains motion consistency in the latent space, ensuring smooth and realistic transitions between frames. Additionally, Grip introduces 2 virtual hand sensors. A is an ambient sensor for detecting object's shape and proximity. B is a proximity sensor for fine-grained contact details, and C is a result of recomputing the proximity sensor values for RNet. Grip was evaluated on datasets like Grab and Intercap and demonstrated superior performance. It generalizes well to unseen objects and produces realistic hand motions. Compared to ManimNet, authors' previous work, Grip achieves higher realism and physical plausibility while running efficiently in real time. This method has significant applications in AR/VR, gaming, and animation, where realistic hand-object interaction is essential. Grip can also be used to enhance existing motion capture dataset by adding natural hand movements, making it a powerful tool for human-object interaction research. In summary, Grip is a data-driven approach that generates realistic and consistent hand-object interactions by leveraging spatial cues and latent consistency. It efficiently handles both single-hand and bimanual interactions, making it a valuable contribution to the field. Thank you for your attention.